Good morning. Okay, so we're working on two-dimensional motion, and we'll also hit velocity addition today. We'll talk about velocity addition. So the exam Friday covers chapters 1 through 4, but not section 4.4. That's circular motion. We'll just save that when we do all the rest of our circular motion in the next unit. Okay, let's start off with this one. It says a baseball is thrown from point S, that's on the right side of our screen right here, point S. It's being thrown toward home plate, which is over here on the left side of our screen. The dashed line represents the path of the ball. So it says use the coordinate system with up as positive and to the left as positive. And then from the following graphs, select which one is the best fit for horizontal velocity versus time, and horizontal acceleration versus time, and vertical velocity and vertical acceleration. Okay, so one more time. The ball is being thrown from the right side of the page toward home plate on the left side of the page. Up and to the left are positive directions. You're picking the best graph that represents horizontal velocity versus time, horizontal acceleration versus time, vertical velocity versus time, and vertical acceleration versus time. Maybe we should just do one at a time here. Go for it. Let's see, let's do the first one. We're looking at what are we looking at? Horizontal velocity versus time. horizontal velocity versus time. Okay, let's take a look. We had a slight majority here picking A. So let's look at this. So when the ball is first released, it has a big velocity in the y direction, right? And some velocity in the x direction. A little bit later, it's, where is it? It's maybe here. The y velocity is less now, right? Because gravity is acting on it in the vertical direction. So we have a smaller velocity vertical, but in the x direction, what's happened? Nothing. There's no force acting on it in the x direction. So its velocity in the x direction remains the same, has the exact same velocity in the x direction that it had when it left your hand. A little bit later, it's at the top of its path. Its y velocity has gone to 0 at that point, right? And the x velocity has stayed exactly the same. Still has the exact same velocity in the x direction. Now it's starting to come down. It's over here somewhere, halfway down. It has a small velocity in the y direction, and it has the same x velocity it had before. And now it's just about to hit home plate. It has a big velocity in the y direction, downward, and the same exact velocity it had the whole time in the x direction. It never changed. So what's the answer for this one? If to the left is the positive direction, then it was constant and positive the entire way. So there's the graph that represents the horizontal velocity versus time. Okay. And if that's the graph that represents horizontal velocity versus time, which graph represents horizontal acceleration versus time? It would be the derivative of that, right, or the slope of that. So that would have to be C. There's no acceleration at all. 0 acceleration in the horizontal direction. Okay, vertical velocity versus time. Take a look at those choices. I'll set a poll. Okay, so we're answering, what are we answering? Vertical velocity versus time. Okay, let's take a look. Looks good. Most people had I. So it started out with a big positive velocity. It went to 0, and then it goes big in the negative direction. Big positive, 0, big negative. So I looks like a good choice. And what's the acceleration then? If I is the velocity, we take the derivative of that. We get a constant negative number, and that would be B. Okay. All right, let's take a look at this one. It says 2 students throw 2 rocks horizontally from a cliff with different velocities, A and B. Both rocks hit the water below at the same time, but rock B hits farther away from the base of the cliff. Use the coordinate system where up is positive, away from the cliff is positive. The origin is at the top of the cliff where the point of release is. So they've drawn it in right here. Your little XY coordinate system is right there. There's your origin. And fill in the graphs here for vertical and horizontal velocities. And I added 2 more here, vertical and horizontal accelerations. So fill in those 8 graphs based on the coordinate system being the point of release, the top of the cliff, and up and to the right is positive. Why don't we go through them one at a time? Do the horizontal first. Horizontal versus time, velocity, horizontal velocity versus time for both balls or rocks. What are they? Rocks. Both rocks. And then we'll go from there. So let's do rock A. Rock A is thrown horizontally. And does the horizontal speed ever change? No, it does not. So we would get a nice graph, looks something like that, right? It's moving to the right. To the right is our positive direction, and its speed in the horizontal direction never changes. How about B? B would look very similar, but it has a slightly larger speed, right, in the horizontal direction. So it would also be a horizontal line, but slightly higher magnitude, right? Is that a horizontal line? Close enough. Okay, because it's being thrown, the question is, how do you know the speed doesn't change? Because it's in the horizontal direction, there's no acceleration, right? What causes acceleration? Forces. So if the object is moving horizontally, in order for the speed to change in the horizontal direction, there has to be some force in that direction. And if we are ignoring air resistance, there's no force horizontally. The only force acting on this rock when it leaves your hand is the force of gravity, and that points towards the center of the earth. So only the speed in the vertical direction can change because there are no forces, there's no acceleration in the other direction. Air resistance question is, will we learn how to calculate air resistance? Air resistance is just a force. And so we can calculate, when we learn forces, we can just add it in. It's a complicated force because it changes as the object moves. It depends on the speed of the object. Because what is air resistance? It's the collisions of the object with the air molecules. So if the object's not moving very fast, the air molecules, the collision with the air molecules doesn't exert much force on the object. But if the object's moving really quickly, then it's colliding with those air molecules at high speed, then it produces a bigger force. So as the speed of your object increases, the air resistance force increases. So it's a little tricky, but we will be able to calculate it once we learn how to deal with forces. Force from the throw. Question, is there force from the throw? Absolutely, there's force from the throw, but remember, our problems, we have to take them in small chunks, okay? In order for us to analyze what's happening as this thing flies through the air, we can only analyze it when it's flying through the air. So what does that mean? That means the split second after it leaves your hand to the split second before it hits the ground. That's when it's in the air, and that's when we can analyze it. If we want to figure out what's happening during the time that your hand is pushing on it, that's a separate problem, and we'd have to deal with that separately. That's a different acceleration, right? So most of these problems, we call them free fall. The reason we call them free fall is the only force acting on the object is the force of gravity. So you have to start thinking in terms of what time period are we interested in here? So for this problem, it's the split second after it leaves your hand to the split second before it hits the ground or the water. Okay. Good. Now let's do, we just did the horizontal velocities. Why don't we do horizontal acceleration? Quick and easy. If the speed is constant, if the velocity is constant, I should say velocity, then the acceleration will be 0. Okay, let's do vertical velocity versus time. This is just like if we only looked at this part of the motion, right? In our previous problem, if we only looked at this part of the motion, our object starts out moving horizontally with no vertical velocity, and then gravity's pulling on it, so it starts to have a small y velocity, then a bigger y velocity, then a bigger y velocity. So as it moves, the y velocity gets bigger and bigger and bigger, but the horizontal velocity stayed the same, right? Well, that's exactly what we're doing down here. It's the exact same problem. So what happens, our velocity starts out at 0, and then it gets bigger and bigger and bigger in what direction? The negative direction, because up is positive. So it looks something like this, right? And how would the other one look? Exactly the same. Question about the velocity when it hits the ground. So again, we can only do this problem when typically our problems have to have constant acceleration. So that means after it leaves your hand and before it hits the ground, right? It has constant acceleration that whole time, just gravity acting on it. Once it's interacting with the ground, you have the ground here, your object hitting it. Now there's a huge acceleration. The ground is pushing up on it, stopping it. There's a huge acceleration. Maybe we could figure out what's going on there, how much the ground depresses when the object hits it. We could figure out that maybe if we kind of assumed that there was some constant acceleration during that time, but that's a different problem. So we can only deal with one acceleration at a time in our problem. So if there's more than one acceleration, like there is as you're throwing it, there's one acceleration. Once it leaves your hand and it's flying through the air, there's a different acceleration. When it's interacting with the ground, there's a different acceleration. We could split it up and look at each one of those things separately if we had enough information about how long it was in your hand and what distance it moved, and if the acceleration was constant and things like that. We could figure that stuff out, but we'd have to have more information on that part of the problem. Yeah, velocity just before it hits the ground. Question is, why is the slope the same? And the answer is that the force of gravity is the same, right? They both started out with 0 y velocity, and they both had the same acceleration in the y direction. So as they fall, the y velocity is going to be changed the same for both. And so that means, what does that mean? Let's do the next part of the problem. What's the acceleration? Oops. That means the acceleration is the same for both, right? Okay, I think we need to see a demonstration now. That's what I think we need to see. Question about weight. The weight, what does that have we had to deal with weight at all with objects moving? No, right? So it doesn't matter because we'll learn more about this when we get to force and acceleration. But as the weight of the object increases, the force of gravity acting on it increases. So you might think that has a bigger acceleration. But what else increases? The mass of the object. And the mass of the object, we call that inertia. And inertia makes it harder to accelerate something. So as the force of gravity increases, the inertia increases at the same rate. And so the acceleration actually is exactly the same. We'll learn more about that when we get to forces. Okay, so what we're going to watch here is two balls, just like we talked about here. One drops straight down, hits the ground right there. One is given a horizontal velocity, and so it follows a curved path and hits the ground over here. And if they both are released simultaneously, which one hits the ground first? Okay, let's take a look. Oops, hold on. There we go. You ready? This apparatus is going to launch two balls simultaneously. There's a horizontal rod that's spring-loaded. And when it's released, the ball on the left will drop straight down and hit the ground here. The ball on the right is going to get a horizontal push from that rod, and it's going to move off to the right and follow a curved path and hit the ground here. The question is, which one hits the ground first? They both are released simultaneously. One drops straight down, the other moves horizontally. Which one hits the ground first? 3, 2, 1. This time in slow motion. Once more, and we'll pause the video a couple of times on the way down. Okay, and the verdict is same time. Both hit at the same time. And the reason is that we can completely separate vertical and horizontal motion. They are independent of one another. And both of these objects started out with the same vertical velocity, in this case, 0. Both of them had the same acceleration. Both of them had the same distance to fall. They both got there in the same amount of time. Okay? Let's take a look at this one. We're going to launch 2 projectiles simultaneously. A is going to follow a high trajectory, but not go very far horizontally. B is going to follow a low trajectory, but go far horizontally. Which one hits the ground first? In this demonstration, my well-calibrated hands will launch 2 projectiles simultaneously. One will follow a high trajectory, but it won't go very far, and it will land here. The other will follow a low trajectory, but it will go much farther, and it will land here. So pause the video and predict which one will hit the ground first if they both leave my hands simultaneously. Let's watch in real time. Now let's take a look in slow motion. Okay, so the answer is B, and the reason is that the time in the air is completely determined by the vertical motion. In fact, let's do this. We already said, the first case here, we already said that if you drop one and you launch one horizontally, that they hit the ground at the same time, right? We all agree with that. So come down here now, and let's pretend here that this ball is being launched horizontally and follows this path. And there's another one that's just being dropped and follows straight down, right? So those 2 would take the same amount of time to hit the ground. We agree with that? And if we did the same thing over here with B, we had one that was launched horizontally and one just falls straight down. Those 2 would take the same amount of time to hit the ground. We good with that? So if we ignore these that are going horizontally, then obviously, I think we would all agree, if we drop 2 objects, one from a high height and one from a low height at the same time, the one that started higher would take longer to hit the ground, right? So the time is completely determined by the vertical direction. Okay, let's go back to so we've got these 4 cannons. They're all aimed at the same angle, 35 degrees. Cannonballs are all the same shapes and sizes. Oh, but they're different masses. And they exit the cannon. The cannonball exits the cannon with a different speed, with different speeds. 2 of them are the same, but different speeds. Okay, so what are we ranking here? The acceleration of the cannonball when it gets to their peak, at the top of its path, at their highest point, What is the acceleration of the cannonball? So the acceleration at the top what's the only force acting on those cannonballs when they're flying through the air? Gravity, right? So what's the acceleration? The split second the cannonball leaves the cannon? Gravity, downward. As it's traveling through the air, when it gets to its highest point, gravity pointing downward. On the way down, until it hits the ground, gravity pointing downward. So they're all the same. And what is it? 9.8 meters per second squared in the downward direction. Okay. All right, let's do the same problem again, but this time figure out what the or rank them according to the velocity at the top of their path. The velocity. There we go. So are these cannonballs moving when they get to the top of their path? Yes. So is the velocity 0? No, but one component is 0, isn't it? The vertical component. But the horizontal component is not, and it's always the same. So we can figure it out here because they tell us the launch speed and the angle. So because they tell us the launch speed and the angle, so let's just look at A. We've got 80 meters per second and an angle of 35 degrees. That means that in the x direction, we have 80 cos 35 degrees, and in the y direction, our initial speed is 80 sine 35 degrees, but we know the y goes to 0. So all that's left when it gets to the top is the x component. So we can just rank them according to the x components here. And which one is the biggest? The angle is the same. So whichever one has the biggest velocity is going to have the biggest x component, right? If the angles were different, we'd have to do a little calculation. But since the angles are all the same, we don't have to do any calculation. We can just look at the initial velocities. So A is the greatest, followed by D, followed by B and C, which are equal, and they're all greater than 0. Okay? Okay, I'm going to set up a problem here, and then I'm going to give you some equations that I'm going to use to solve the problem, and you're going to tell me where the origin is and what the positive direction is. So if this is our problem, I'm going to throw something down at 30 degrees. This is going to be H. And we'll let okay, so if I'm using this equation, to find the time, maybe I'll put here time. If I'm using this equation to find the time, you tell me where is my origin and what's my positive direction. Okay, so I'm comparing this to this equation. Right, I'm comparing it to this equation. So right off the bat, this minus sign here is telling me that that up is positive, down is negative. So my positive direction is up. And where's the origin? At the top of the cliff, because it started out at y equals 0 and it ended up at negative 50. Okay. Should we do one more? How about this? Origin is the top of the cliff again. And the positive direction this time is down. Okay. You can do that problem later. I got 2.02 seconds, and X final is 52.3 meters. I didn't do V final, but you can check your answers later. Okay, let's see, let's do one more. So we've got a kicker. It's going to kick a ball. And this is the goal post. It's a horizontal bar there. And we want to know if the okay. So if we're given and we also want to know when it gets to the plane of the goalpost, wherever it is there, is it still on its way up, or has it passed its peak and it's coming down? Okay, so we need to be given some information here, right? So if we're given V initial is 25 meters per second, and theta 30 degrees, and X final is 40 meters away, and the height of that goalpost is 3 meters. Okay, so why don't we take a little break, and we'll finish the problem when we come back. How does that sound? So 10 minutes, we'll come back at 11. I'll pause the recording. All right. So we want to fill in our chart, but before we do that, we have to pick an origin and define our positive directions. I'll just pick the starting position. Well, I've sort of already put in 0 and X final. I guess I picked the origin already. Okay. Once we do that, we can fill in our table. Or I guess I should say tables, because this is a two-dimensional problem. We do X and Y. We've got our initial and final position. Really, we care about the change in position, but I usually write it this way. We've got our velocity initial in the X, velocity final, acceleration, time. Excuse me. So let's fill in what we know. We know it starts at X equals 0. And there are a few ways to approach this, but I think the best way is just let's plug in X final, you know, the plane of the goalpost, and this plane right here, and see what, and then we'll solve for Y. So we'll just, when it gets to X final, then we'll solve for Y and see if it's more than 3 or less than 3. So X initial would be 0, and X final would be 40 if we take that approach, right? And we know that this thing is launched with an initial speed of 25 meters per second. So the X is going to be 25 cos 30 degrees, and the Y initial speed is 25 sine 30 degrees. So that means I've got this becomes 21.7, I think. Is that right? And this would also be 21.7 because the acceleration in the X direction is 0. Y initial is 0. Y final, we don't know. That's what we're interested in. We know the initial velocity in the X direction is 12.5. V final, we don't know. Acceleration minus 9.8. And time, we don't know. So we'll find time from the X direction. That's going to be 40 meters over 21.7 meters per second. $1.85. Now we plug that. Okay, confirmation, excellent. We plug that value in to our Y direction. And we get So it's way over the bar. Way over the bar. And then the question is it going up or is it coming down? And there are a number of different ways to do this. So I think the easiest one is to find V final. Find V final. If V final is negative, it's coming down because we chose up as our positive direction. If V final is positive, it's still on its way up. There are other things you could do. $1.37 might be. Might be. There are a couple of other things you could do because you could find, where were we? We were at 1.85 seconds. It took 1.85 seconds to get there. You could plug in 1.84 seconds and 1.86 seconds and see if you're getting Y final is higher or lower. What's happening to Y final? Is it going down as this time changes a little bit, or is it going up? Right, that's another technique you could use. I'm being told this is 3.7. Is that better? Okay. And so those are a couple of techniques. I say let's just find Y final. Sorry, V final. But if we find V final, you have to be careful. Can we use this equation? Oops. Can we use this equation? No, because it doesn't tell us the sign of V final, right? We have to, when we take the square root at the end, it could be positive or negative. We don't know. We would have to know the sign from other information in the problem. And we're trying to use the equation to get the sign of V final. So we can't use this equation. So we would use something like this one. Is that right? So I got negative. Okay, good. Okay, let's do velocity addition. So the idea here is that different observers may measure speeds differently depending on their relative motion. So a simple example is somebody on a train, right? So maybe nothing is moving compared to them. If I'm holding something in my hand and I'm sitting in a train moving, I look at that object and I say, that object's not moving. I measure its speed to be 0 because it's not moving with respect to me. But as we go by, you if you're not on the train, you see that object moving with the same speed of the train, with the same speed of me, right? So you measure the velocity of that pen to be different than I would measure it, because I just see it as being at rest, it's stationary. So that's velocity addition. We can transform the velocity from one frame of reference to another. So we'll start off, let's just do a couple of simple ones where we only have motion in one dimension. So we've got our person on a flat train car here, and the train is moving. Velocity of the train with respect to the ground is 24 meters per second, and the velocity of our person with respect to the train is 8. Okay. So we want to know, if you're standing on the train car, right, watching the person run, you're measuring their speed to be 8 meters per second. They're moving, that's how fast they're measuring their speed to be. But if you're standing off on the side watching that person run, you measure their speed to be a little different, right? So what's the velocity of the person with respect to the ground? And we have this little technique we use, and I know this is pretty straightforward, but let's go ahead and use a formal technique first, and you'll see as the problems become more complicated, it's nice to have that framework. So the velocity of the person with respect to the ground is the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. It's a vector addition problem. Okay, we're adding vectors. In this case, the vectors are all horizontal. So it makes it much easier to add them that way, but that's okay. We'll start with this and then we'll move to two-dimensional cases. Boats crossing rivers and airplanes flying through the air and things like that. So we start with the velocity of the person with respect to the train. That's this vector here, 8. And then we're going to add to that the velocity of the train with respect to the ground. That's this one here. What did I say that was, 8? That means I have to go just a little bit more. There we go. And so I add those two together and I get my result, the velocity of the person with respect to the ground. So it would be 16. (16 meters per second to the right. That makes sense? If the person was not moving at all with respect to the train, if they were just standing on the train and you were standing on the ground, you'd see them flying by at 24 meters per second to the right. But they're moving slightly to the left, so it makes it appear that they're moving a little bit slower than 24 meters per second to the right. It looks like they're only moving 16 meters per second. Okay, let's do now in this case, question is, wouldn't the velocity be larger than 24? No, because they're moving opposite the direction of motion. Think about it this way. If you had, well, let's just do the example here. Let's do this one. We've got our person moving in the same direction as our train. Let's have this to be 20 and this be 12. So go ahead, do it using vector addition first. So we've got 12. And then we're adding to that this vector. What is this? 6, 12, 18. And our resultant is 32. So they're moving 32 meters per second to the right. Does that clear up the previous one? Okay, one more. We've got our train moving to the left. Person moving to the right. So you could probably do that in your head. Trains moving to right at 5 meters per second. Thank you for asking that question. We'll take a look at that next. Take a look at that next. I have the ultimate video for you. Okay, V person ground is V person train plus V train ground. Get in the habit of thinking along these lines. So the person with respect to the train is 10. So I'll go 5, 10. The train ground is 30. 5, 10, 15, 20, 25, 30. And so we get 20, right? 5, 10, 15, 20. That's a G. So I'm not defining positive directions. I'm just giving you the direction with an arrow here. Okay. I could have defined positive direction. I could have said to the right is positive, and then this one would be a positive 32, and this one would be negative 20. But I'm just giving it to you in words, or I guess pictures, arrows. So I could have defined positive directions and just used plus and minuses. Yes. Okay. Let's take a look at this video. Didn't want to do that. Okay, hold on.
果たして時速100キロで
Okay.
果たして時速100キロで走行する車から進行方向と逆の方向へ時速100キロのボールを投げると一体ボールはどのように動くのか。
Okay, is it all clear now? You got it? We've got a little truck with a pitching machine mounted in the back of it. Pitching machine is going to be well calibrated to launch the ball at 100 km per hour. And the truck is going to be driving 100 kilometers per hour. And we'll see what happens to that ball. Okay. This is kind of like a Japanese Mythbusters, I guess.
実際に調べてみた。今回検証の舞台に選んだのは大分県にあるオートポリスサーキット場。そしてトラックの荷台には時速100キロでボールを投げられるピッチングマシーンをしっかり固定。
Okay, so we're setting the stage here. Oh, don't worry, it gets better.
なお時速100キロのスピードを出していただくトラック。
Okay, I know you want to make sure everything is on the up and up, right? So they're showing us his driver's license here. You got that? They're showing us his driver's license. It's okay. He's licensed to drive this truck.
スピードを出していただくトラックの運転には国内 A 級ライセンスを持つ松浦さんに依頼。検証方法はまずトラックで時速100キロのスピードを出すためコースを一周。そして再びスタートした地点に時速100キロのスピードで戻ってくる。そこでスタートラインを通過した瞬間にボールをトラックの進行方向と逆方向へ発射。この時ボールはどのように動くのかを調べる。
Okay, here we go.
トラックをスタート位置につかせ。
So we've got this nice black background, so that ball will show up against it. This is on the straightaway, as they just showed you. So here goes.
スピードガンを使用し正確に時速100キロのボールを投げられるよう調整に入る。そして
まだ球が
Okay, so he's got it dialed in perfectly, 100 km per hour on the radar gun.
本当に100キロ出てる。
準備完了。
ぴったり100だ。
ちなみにこちらが停止状態のトラックから時速。
So that's what it looks like when the truck is not moving, right? It just fires out there, and then they've got it in super slow motion here.
100キロで投げたボールの動きである。検証開始。
What's wrong with this picture? The guy inside the truck is wearing the helmet.
シグナルがネットからブルーへ。今トラックがスタートです。時速100キロのスピードを出すためにトラックがシフトチェンジ、徐々に加速していきます。
120までしか切ってないじゃない。
果たして時速100キロで走行する車から進行方向と逆の方向へ時速100キロのボールを投げるとボールはどのように動くんでしょうか。さあスタート地点に今再びトラックが戻ってきました。最終コーナーを立ち上がってこれが最後のストレート。現在トラックの時速は100キロです。今時速100キロでトラックがここまで戻ってきました。さあトラックが時速100キロをキープしてスタートラインへと向かっていきます。そしてこちらも今ピッチングマシンにボールをスタンバイ。そして 投げました。投げました。
果たして時速100キロで走行する車からボールはどのように動くのか。
Now it jumps to a black and white montage here. I don't know why, but there we go. Countdown.
投げました。ボールがコース上を転がっています。一体ボールはどのような動きをしたんでしょうか。さあスロー映像で確認してみましょう。
そうだ、総裁か。マジでそんなことになるんだ。
ご覧ください。ボールは投げた地点で落ちています。時速100キロで走行する車から進行方向と逆の方向へ時速100キロのボールを投げると、なんとボールは投げた地点で落下しました。
Pretty good, right? The car was almost the exact same speed.
100キロで走行。
So here's
ご覧ください。ボールは投げた地点で落ちています。時速100キロで走行する車から進行方向と逆の方向へ時速100キロのボールを投げると、なんとボールは投げた地点で落下しました。
But they nailed that one. Okay. Moral of the story is this stuff works, right? The car's going 100 km per hour. You're throwing the ball 100 km per hour with respect to the car in the other direction. With respect to the ground, it's not moving at all, right? It just hangs there. Okay, so let's make this a little more interesting. What we're doing here with one dimension, with the car train moving in one dimension, not very exciting. Let's do 2 dimensions. So our formula is this: if the velocity of A, this is the velocity with respect to C, this is the velocity of C with respect to B, and we want to know the velocity of A with respect to B. Okay, we know the velocity of A with respect to C. We know C with respect to B. We want to know A with respect to B. So the formula is the velocity of A with respect to B is the velocity of A with respect to C plus C with respect to B. This is a vector addition formula. So the first one has to be the same. The first subscript has to be the same. Ah, okay. Was it like a Japanese Mythbusters? They would test different things. We're getting first-hand response here. Very popular show about 15 years ago. Okay. So the first subscript has to be the same. The last subscript has to be the same. And the 2 in the middle have to be the same. And if you line it up like that, it tells you how to add these vectors. Sometimes you need to subtract the vectors to get the right answer. Sometimes you need to add them. This formula tells you whether you're adding or subtracting. So let's do a quick example or 2. Let's do a, what should we do? Boat crossing a river. So we'll make the velocity of the water with respect to the ground 2 meters per second, and we'll make it uniform across the whole river, unlike a real river, right? A real river, the water flows fastest in the center and slowest near the banks, but we'll just make our water have the same speed everywhere across the whole river. And we're going to launch a boat. We're going to launch a boat from here. And the boat is going to point due north. What is this? Sure, straight up. So the boat is always going to have its direction pointed straight up, which means that where is it going to end up? It's not going to end up over here, is it? It's going to end up down here somewhere, because the water, as the boat is trying to get across, the water's pushing on it, and so it's going to end up downstream. It's not compensating for the flow. So this is the velocity of the boat. And how does a boat measure its velocity? With respect to what it's moving through, right? With respect to the water. And we'll make that 5. Related rates. I'm not familiar with that term. I'm not sure about that. Okay, so what are we going to do? We want to know the velocity of the boat with respect to the ground. Okay. So the velocity of the boat with respect to the ground is the velocity of the boat, with respect to the water, plus the velocity of the water with respect to the ground. This is a vector addition problem. So the first vector we know, I'll use blue. The first vector we know, right, it's this one right here. So I'll just draw that. The second vector we know, that's this vector here, right? So I'll just draw that in here. One, two, three, four, five, 1, 2. Yeah, so I'm trying to draw this to scale. And so the third vector is going to be the sum of those two. It's going to be this right here. So the magnitude, we can get the magnitude of this vector, right? Because I gave you an easy one. It's a right triangle. And we can get the angle. And so we're done with this problem, right? We can figure out the speed, the magnitude of the velocity, and we can figure out the angle. And again, with these problems, I usually tell people a picture is worth 1,000 words. If you draw this picture for me here and give me those, you're telling me what theta is, you're giving me some angle here, you're indicating on here what theta is, right? So I know exactly what it is. You don't have to use a whole bunch of words, north of south, east of west. I don't, you know, it gets really complicated trying to describe angles with words. Draw a little picture, tell me what theta is on your diagram. It's that angle right there, and then give me a number, right? And then it's super easy. I know exactly what you found. I know you know what you found. I know what you found. Everybody knows, right? It's good. So this is one of those situations, or a picture is worth 1,000 words. Okay, let's make it more interesting, shall we? Doesn't have to be a right angle. Let's take our same boat, same river. This time, our boat is angled at 30 degrees. Oh yeah, this is vector addition problem. I think the question is, this vector addition. So when you add vectors, you add them tip to tail, right? You draw your first vector, then you go out to the tip of that vector, that's your new origin. Then you draw your second vector, and you keep doing that until you have all your vectors drawn. And then what's your answer? Your answer is from your starting point to your ending point. That's your final answer, right? Okay, so this time we're given that the boat is angled at 30 degrees. And we want to know, where does it, what's the velocity find? Okay, so this time it's angled at 30 degrees. So we know that V boat ground, V boat water plus V water ground, right? And so this one is a little tricky. So if if I draw my first vector, I'll use blue, a distance of 5 at 30 degrees, let's say it's something like that. Then I draw my second vector. I'm not really taking measurements here. I think if I did do it with measurements, it would end up like that. And so where's my answer? My answer is going to end up being just a little bit upstream of straight across the river. It's not going to be straight across the river. It's going to be a little bit upstream. Okay, so I think the best thing to do is just use components, right? So I would make a chart here. So let's pick an X and Y direction. I'll call this my X direction and this my Y direction. So this would be X and this would be Y. So I've got the velocity of the boat with respect to the water. That's moving at, what is it? It's going to be to the left, so minus 5 sine 30 degrees and plus 5 cos 30 degrees. Did I get that right? Here's my 30-degree angle. So in this direction, which is my y direction, right? It's moving 5 cosine 30 in the positive direction. And in the other direction, it's moving 5 sine 30, and that would be the negative, right? My positive direction is to the right. That would be my negative x direction. So negative 5 sine 30. We okay with that one? Then I've got my V water ground. That's moving 2 meters per second to the right. That's my positive x direction. And it has no velocity in the y direction, right? And so what do? I add those up. And I get the velocity of the boat with respect to the ground. And so this is going to be 2 minus 2.5. And this one's going to be 5 cos 30, which is 4.3 about. So it's going 4.3. If we draw it out, it's 4.3 in this direction and a half in that direction. Didn't want that. Go away. There we go. There we go. And so this is V boat ground, and we can find the magnitude of that. And we can find the angle. Okay. So you're probably wondering why you need this formula. We just keep adding these vectors together, right? Well, let me give you an example where we have to subtract vectors. 2 cars approach an intersection. So we've got car A coming this way, and car B coming this way. Okay, that's as good as it gets. Those are cars, not turtles. V A G is the velocity of car A with respect to the ground. How does a car measure its velocity? With respect to the ground, right? So this is going to be 50 miles per hour due east. And the velocity of B with respect to the ground is, let's make that 40 miles per hour due north. And we want to find the velocity of car A, no, the velocity of car B with respect to car A. Okay. So if you were sitting in car A, what would it look like car B was doing? It's a question, right? And it's a good idea to think about these things. So this, I'm using this north, right? That's my coordinate system. Okay, so it's a good idea to think about your answer ahead of time. That way, if you get a vector that points to the wrong quadrant or something, you know you've made a mistake with the sign, you added instead of subtracted or something, right? So what do we expect our answer? If we were sitting in car A, what does it look like car B is doing? It looks like it's coming right toward us, right? Hopefully not right toward us, or our imaginary cars are going to have an imaginary collision when they get to that intersection. But pretty close, right? These cars are approaching, they're approaching an intersection. They're going to get there roughly the same time. Hopefully they miss each other. And so if you're sitting in car A, it looks like car B is coming toward you, basically, right? So our answer, we expect our answer to be something like this. Right, something like that. Something that points up and to the left, from B to A, right? So let's see what we get here. So our formula, the velocity of B with respect to A, that's what we want. Our formula tells us it's the velocity of B with respect to the ground plus the velocity of the ground with respect to A, right? The first subscript has to be the same. The last subscript has to be the same. The two in the middle have to be the same. So this is our formula. So let's start doing it. So the velocity of B with respect to the ground, that's given. Use blue for that. 40. So 10, 20, 30, 40. In this direction, right? Then we want to add the velocity of the ground with respect to A. But that's not given. What's given is A with respect to the ground. So how do we flip it? Well, the velocity of A with respect to the ground is the opposite of the velocity of the ground with respect to A. It flips by 180 degrees, right? Because if I'm moving this way, if I'm walking this way at 1 meter per second, I don't think I'm moving. I look over and I see you, and I think you're moving 1 meter per second that way. But you don't think you're moving. You look at me, you think I'm moving 1 meter per second this way. So your velocity with respect to me is negative of my velocity with respect to you, right? We see it opposite. So that negative sign tells us it's flipped 180 degrees. So so what we need to do here is add, so the velocity of A, let me just I'll pencil it in. The velocity of A with respect to the ground is this one. 1, 2, 3. That's the velocity of A with respect to the ground. But we want the ground with respect to A, which is negative A ground. We want this one. This is the velocity. This is negative. Darn. Hate when that happens. One note died. There we go. Now I have to share it again. Okay, we're back. This is negative A ground, which is the same as ground A. Now, my answer is this vector right here. Oops, I didn't want that color. Why does it keep giving me that color? That's my answer. Okay, so that's why we use this. That's why we use this equation. It's sometimes you're adding the vectors. Sometimes you have to subtract a vector. The equation tells you whether you have to add or subtract. But the idea is that this is a vector addition problem. Don't just add up components blindly. You have to do it carefully, split them into components before you add them, things like that, okay? Don't just add numbers like vectors like they're numbers. Okay? So practice those a little bit, practice two-dimensional kinematics. We'll do more next time, but I wanted to make sure we got this in today because I didn't want to give you new information the day before an exam, right? So this is the last of the new information. We'll fine-tune some things next time, and the exam will be Friday. Okay? I'll stick around for a few minutes if anybody have questions. So I'll stop the recording now, and also there will be